Let's talk about how to set up a reaction table or an ice table for a pH calculation with something called a common ion. So up until now, our discussion of acid-base ionization in the past topics was limited to solutions containing a single solute. We just had a dilute weak acid solution or dilute weak base solution. But in this topic, in these reactions, what we will do is consider the acid-base properties of a solution that has two different dissolved solutes. So here we've got a solution that is ethylamine, so we have a weak base, and then we have also in this solution another solute. So they give us the concentration, and we have ethyl ammonium chloride. So we got two solutes that have been added to this particular solution. Now, where the term common ion comes into play here is when you look at these two solutes, when the solutes in solution contain the same ion, whether it's a cation or an anion, then we have what we call a common ion, and then the common ion effect comes into play. So let's look more closely at what this common ion effect is. So look at this first example here. We have a solution that has two different solutes here. So you may notice that we have a weak acid here, here's acetic acid, and we also have this strong electrolyte, sodium acetate. So if I take sodium acetate and I put it in water, it will dissolve. And as a strong electrolyte, what do they do? Strong electrolytes, unlike weak acids or weak bases, typically ionize pretty much 100%. So this reaction is just unidirectional as I've written it. It's going to ionize into acetate ion and sodium metal ion. Okay? Now also in the solution, we have acetic acid, which is a weak acid. By definition, weak acids do not ionize 100%. As a matter of fact, as long as the solution isn't too dilute, they ionize to a very small extent. So acetic acid ionizes slightly, and the result of its reaction with water molecules is acetate ion and hydronium ion, or H+. Now look at the products of these two reactions. Here we've got the dissolving of the strong electrolyte in water, sodium acetate. We get acetate as an ion here produced. Well, look at the ionization of acetic acid. We also get acetate as a product here, the acetate ion. Now, if you remember from previous chapters, previous topics where we talked about equilibrium and Le Chatelier's principle, well, what's going to happen, do you think, when the concentration of acetate ions is increased in solution as a result of the sodium acetate that's been added? Well, as the concentration of this increases, this reaction here, which is in equilibrium, is going to be pushed to the left. So essentially, by adding this to solution, I'm going to further suppress the ionization of this weak acid, which means I'm going to have less of this, less hydronium, and more of this than I normally would if there were not any sodium acetate at all. So again, just to re-summarize that, without sodium acetate in solution, then this acetic acid will react with water and ionize to a certain extent. But because this solution also has a second solute added to it, sodium acetate, and this solute is a strong electrolyte, which means that it will dissociate completely 100% into acetate ion and sodium metal ion. This acetate ion will cause this reaction to shift to the left, more to the left, because the concentration of acetate is now increased in solution. Because these two are common ions. This is the common ion effect. The common ion effect is the shift in equilibrium from right to left caused by the addition of a compound, this second solute, that has an ion in common with the dissolved substance. Now, this common ion effect also applies to solutions that have weak bases as well. So here we have a weak base, ammonia, And if I also add to this solution a second solute, this is a strong electrolyte, cation, anion. It's ammonium chloride. When dissolved in water, dissociates completely as a strong electrolyte into ammonium ion and chloride ion. Well, ammonium is an ion produced here. It's a cation, whereas here is an anion, but it doesn't matter. It's an ion. Ammonia, when it reacts with water molecules, ionizes into ammonium, and we also get hydroxide produced as a result of that reaction. The common ion here is ammonium, the cation. And so because the concentration of ammonium in solution is increased due to the dissolving, the addition of ammonium chloride to solution, then this reaction, the equilibrium is going to shift from right to left, which means we will get less ionization of ammonia. So essentially what this means is, due to the common ion effect, a solution that has both acetic acid and sodium acetate will be less acidic than it would be if it just had acetic acid in it. Why? Again, because of the addition of this sodium acetate to solution, the equilibrium here is going to shift to the left, which means that we end up with less hydronium ion concentration, and that is what determines acidity and pH. Yes, even though we have sodium ion here in solution, that's not going to have any effect on the pH of this solution. The charge of this sodium ion is just too little to react with water molecules. Furthermore, the addition of this is not going to increase hydronium ion concentration either. When we look at the bottom example here with our weak base, well, the addition of ammonium chloride to solution is going to make this solution less basic than what it would be if it only had ammonia in it. Remember, a basic solution has a high concentration of hydroxide ions, or the concentration of hydroxide ions is greater than the concentration of hydronium ions. Well, because we have a common ion here, then the equilibrium of this reaction, the ionization of ammonia, is shifted to the left, which means the concentration of our hydroxide ions is going to decrease and the solution will be less basic. So now let's take this information and apply it here to this topic. So if we're going to construct an ice table in order to calculate pH for this solution, then we need to determine what the major species at play are in this solution. And we determine that by writing out the reactions. So here are the two reactions at play. The first reaction here is the base protonation reaction between our weak base, ethylamine, and water. In this reaction, this is our base, water is acting as our acid, and donates a proton to ethylamine. And so we end up with this conjugate acid of our weak base, and here we have hydroxide, which is the conjugate base of this acid. And this reaction occurs until it establishes or reaches an equilibrium. Now we have another reaction as well, because we have in this solution again this second solute, this strong electrolyte. This strong electrolyte is dissolved in this solution to this concentration, and when it dissolves in water, what it does is dissociate into these two ions, this cation and this anion. So we have chloride anion and we have this cation here. The reason this matters is because when we fill out our ice table, well, the initial concentration of our conjugate acid is not going to be zero like it has been in the past. Initially, our concentration of this conjugate acid to our base is going to be whatever the concentration of this is. So let's fill this table out from the beginning. Let's check first our initial concentration of our weak base. Well, that's given here in the problem. It is 0.0 0.46 molar. So that is the initial concentration. Okay. The change in concentration, well, as this reaction here proceeds, the concentration of this is going to decrease to some small extent. So it's going to be minus X. I check the stoichiometry of the reaction. Everything is balanced, and there's a coefficient of 1 here, so it's just minus X. Okay, so the final concentration of this will be 0.46 minus X. Initially, our concentration of this conjugate acid to our base is the concentration of this and also this. What is the concentration of ethyl ammonium chloride in solution? It is 0.44 molar. The reason these two are equal is because this is a strong electrolyte and this reaction goes to completion. So if I start with 1 mole of this, I end up with 1 mole of this. If I have 2 moles of this, I have 2 moles of this. Or if I have 0.44 moles of this, I have 0.44 moles of this. So assuming I have 1 liter, then there would be 0.44 moles. The concentration is 0.44 molar, so the concentration of this initially will be 0.44 molar. As this process reaches equilibrium, the concentration of that will increase to some amount, and so the final concentration will be this plus X at equilibrium. So for hydroxide, the initial concentration will be 0 because hydroxide is only produced in this reaction, the protonation of our weak base. The change will be plus X, and the final concentration at equilibrium will be plus X. This will be your final answer. So if they asked us to calculate pH, well, because this is a weak base, you would use hydroxide ion concentration. And so in this case, particular case, X stands for the change in the hydroxide ion concentration. Now, if this were a weak acid instead of a weak base, the process would be the same, except we'd look at the reactions through this lens, and X would be equal to the change in the hydronium ion concentration.